A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. A natural number greater than 1 that is not a prime number is called a composite number. For example, 5 is prime because 1 and 5 are its only positive integer factors, whereas 6 is composite because it has the divisors 2 and 3 in addition to 1 and 6. The fundamental theorem of arithmetic establishes the central role of primes in number theory. Any integer greater than 1 can be expressed as a product of primes that is unique up to ordering. The uniqueness in this theorem requires excluding 1 as a prime because 1 can include arbitrarily many instances of 1 in any factorization, e.g. 3, 1, 3, 1, 1, 3, etc. are all valid factorizations of 3. The property of being prime is called primality, a simple but slow method of verifying the primality of a given number and is known as trial division. It consists of testing whether n is a multiple of any integer between 2 and. Algorithms much more efficient than trial division have been devised to test the primality of large numbers. These include the Miller-Rabin primality test, which is fast but has a small probability of error, and the AKS primality test, which always produces the correct answer in polynomial time but is too slow to be practical. Particularly fast methods are available for numbers of special forms, such as Mersenne numbers. As of January 2016, update, the largest known prime number has 17,425,170 decimal digits. There are infinitely many primes, as demonstrated by Euclid around 300 BC. There is no known useful formula that sets apart all of the prime numbers from composites. However, the distribution of primes, that is to say, the statistical behavior of primes in the large, can be modeled. The first result in that direction is the prime number theorem, proven at the end of the 19th century, which says that the probability that a given, randomly chosen number n is prime is inversely proportional to its number of digits, or to the logarithm of n. Many questions regarding prime numbers remain open, such as Goldbach's conjecture, and the twin prime conjecture. Such questions spurred the development of various branches of number theory, focusing on analytic or algebraic aspects of numbers. Primes are used in several routines in information technology, such as public key cryptography, which makes use of properties such as the difficulty of factoring large numbers into their prime factors. Prime numbers give rise to various generalizations in other mathematical domains, mainly algebra, such as prime elements and prime ideals. Definition and examples. A natural number is called a prime number if it has exactly two positive divisors, 1 and the number itself. Natural numbers greater than 1 that are not prime are called composite. Among the numbers chapter 1 to 6, the numbers chapter 2, 3, and 5 are the prime numbers, while 1, 4, and 6 are not prime. 1 is excluded as a prime number, for reasons explained below. 2 is a prime number, since the only natural numbers dividing it are 1 and 2. Next, 3 is prime. 2, 1 and 3 do divide 3 without remainder, but 3 divided by 2 gives remainder 1. Thus, 3 is prime. However, 4 is composite, since 2 is another number dividing 4 without remainder. 4 equals 2, 2. 5 is again prime. None of the numbers chapter 2, 3, or 4 divide 5. Next, 6 is divisible by 2 or 3, since 6 equals 2, 3. Hence, 6 is not prime. The image at the right illustrates that 12 is not prime. 12 equals 3, 4. No even number greater than 2 is prime because by definition, any such number n has at least 3 distinct divisors, namely 1, 2, and n. This implies that n is not prime. Accordingly, the term odd prime refers to any prime number greater than 2. Similarly, when written in the usual decimal system, all prime numbers larger than 5 end in 1, 3, 7, or 9. Since even numbers are multiples of 2, and numbers ending in 0 or 5 are multiples of 5, if n is a natural number, then 1 and n divide n without remainder. Therefore, the condition of being a prime can also be restated as: a number is prime if it is greater than 1 and if none of 2, 3, n-1 divides n. Yet another way to say the same is: a number n greater than 1 is prime if it cannot be written as a product of two integers a and b, both of which are larger than 1. n equals ab. In other words, n is prime if n items cannot be divided up into smaller equal-size groups of more than one item. The set of all primes is often denoted by p. The first 168 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, 101, 103, 107, 109, 113, 127, 131, 137, 139, 149. 151,157, 163, 167, 173, 179, 181, 191, 193, 197, 199, 211, 223, 227, 229, 233, 239, 241, 251, 257, 263, 269, 271, 277, 281, 283, 293, 307, 311, 313. 317,331, 337, 347, 349, 353, 359, 367, 373, 379, 383, 389, 397, 401, 409, 419, 421, 431, 433, 439, 443, 449, 457, 461, 463, 467, 479, 487, 491, 499. 503,509, 521, 523, 541, 547, 557, 563, 569, 571, 577, 587, 593, 599, 601, 607, 613, 617, 619, 631, 641, 643, 647, 653, 659, 661, 673, 677, 683, 691. 701,709, 719, 727, 733, 739, 743, 751, 757, 761, 769, 773, 787, 797, 809, 811, 827, 821, 823, 827, 829, 839, 853, 857, 859, 863, 877, 881, 883, 887, 907, 911,919, 929, 937, 941, 947, 953, 967, 971, 977, 983, 991, 997. Fundamental theorem of arithmetic. The crucial importance of prime numbers to number theory and mathematics in general stems from the fundamental theorem of arithmetic, which states that every integer larger than 1 can be written as a product of one or more primes in a way that is unique except for the order of the prime factors. Primes can thus be considered the basic building blocks of the natural numbers. For example, as in this example, the same prime factor may occur multiple times. A decomposition. N equals P1, P2. Pt of a number n into prime factors P1, P2 to Pt is called prime factorization of n. The fundamental theorem of arithmetic can be rephrased so as to say that any factorization into primes will be identical except for the order of the factors. So, albeit there are many prime factorization algorithms to do this in practice for larger numbers, they all have to yield the same result. If P is a prime number and P divides a product hab of integers, then P divides her or P divides B. This proposition is known as Euclid's lemma. It is used in some proofs of the uniqueness of prime factorizations. Primality of 1. Most early Greeks did not even consider 1 to be a number, so they could not consider it to be a prime. By the Middle Ages and Renaissance, many mathematicians included 1 as the first prime number. In the mid-18th century, Christian Goldbach listed 1 as the first prime in his famous correspondence with Leonhard Euler, who did not agree. In the 19th century, many mathematicians still considered the number 1 to be a prime. For example, Derek Norman Lamer's list of primes up to 10,006,721, reprinted as late as 1956, started with 1 as its first prime. Henry Lebesgue is said to be the last professional mathematician to call 1 prime. By the early 20th century, mathematicians began to accept that 1 is not a prime number, but rather forms its own special category as a unit. A large body of mathematical work would still be valid when calling 1 a prime, but Euclid's fundamental theorem of arithmetic would not hold as stated. For example, the number 15 can be factored as 35 and 135, if 1 were admitted as a prime. These two presentations would be considered different factorizations of 15 into prime numbers. So the statement of that theorem would have to be modified. Similarly, the sieve of Eratosthenes would not work correctly if 1 were considered a prime. A modified version of the sieve that considers 1 as prime would eliminate all multiples of 1 and produce as output only the single number 1. Furthermore, the prime numbers have several properties that the number 1 lacks, such as the relationship of the number to its corresponding value of Euler's tangent function or the sum of divisors function. History. There are hints in the surviving records of the ancient Egyptians that they had some knowledge of prime numbers. The Egyptian fraction expansions in the Rhind papyrus, for instance, have quite different forms for primes and for composites. However, the earliest surviving records of the explicit study of prime numbers come from the ancient Greeks. Euclid's elements contain important theorems about primes, including the infinitude of primes and the fundamental theorem of arithmetic. Euclid also showed how to construct a perfect number from a Mersenne prime. The sieve of Eratosthenes, attributed to Eratosthenes, is a simple method to compute primes. although the large primes found today with computers are not generated this way. After the Greeks, little happened with the study of prime numbers until the 17th century. In 1640, Pierre de Fermat stated Fermat's little theorem. Fermat also conjectured that all numbers of the form 22n plus 1 are prime, and he verified this up to n equals 4. However, the very next Fermat number 232 plus 1 is composite, as Euler discovered later, and in fact no further Fermat numbers are known to be prime. The French monk Marin Mersenne looked at primes of the form 2p-1, with p8 prime. They are called Mersenne primes in his honor. Euler's work in number theory included many results about primes. He showed the infinite series 1/2 plus 1/3 plus 1/5 plus 1/7 plus 1/11 plus is divergent. In 1747 he showed that the even perfect numbers are precisely the integers of the form 2p-1, where the second factor is a Mersenne prime. At the start of the 19th century, Legendre and Gauss independently conjectured that as x tends to infinity, the number of primes up to x is asymptotic to x, lane, where lane is the natural logarithm of x. Ideas of Riemann in his 1859 paper on the zeta function sketched a program that would lead to a proof of the prime number theorem. This outline was completed by Hadamid and de la Vallée-Poussin, who independently proved the prime number theorem in 1896. Proving a number is prime is not done by trial division. Many mathematicians have worked on primality tests for large numbers, often restricted to specific number forms. This includes Pepin's test for Fermat numbers, Proth's theorem, the Lucas-Lehmer primality test, and the generalized Lucas primality test. More recent algorithms like APRTCL, ECPP, and AKS work on arbitrary numbers but remain much slower. For a long time, prime numbers were thought to have extremely limited application outside of pure mathematics. This changed in the 1970s when the concepts of public key cryptography were invented, in which prime numbers formed the basis of the first algorithms, such as the RSA cryptosystem algorithm. Since 1951, all the largest known primes have been found by computers. The search for ever larger primes has generated interest outside mathematical circles. The Great Internet Mersenne prime search and other distributed computing projects to find large primes have become popular, while mathematicians continue to struggle with the theory of primes. Number of prime numbers. There are infinitely many prime numbers. Another way of saying this is that the sequence 2, 3, 5, 7, 11, 13 of prime numbers never ends. This statement is referred to as Euclid's theorem in honor of the ancient Greek mathematician Euclid, since the first known proof for this statement is attributed to him. Many more proofs of the infinitude of primes are known, including an analytical proof by Euler, Goldbach's proof based on Fermat numbers, Furstenberg's proof using general topology, and Kummer's elegant proof. Euclid's proof. Euclid's proof considers any finite set S of primes. The key idea is to consider the product of all these numbers plus 1. Like any other natural number, n is divisible by at least one prime number. None of the primes by which n is divisible can be members of the finite set S of primes with which we started, because dividing n by any one of these leaves a remainder of 1. Therefore, the primes by which n is divisible are additional primes beyond the ones we started with. Thus any finite set of primes can be extended to a larger finite set of primes. It is often erroneously reported that Euclid begins with the assumption that the set initially considered contains all prime numbers, leading to a contradiction, or that it contains precisely the n smallest primes rather than any arbitrary finite set of primes. Today, the product of the smallest n primes plus 1 is conventionally called the nth Euclid number. Euler's analytical proof. Euler's proof uses the sum of the reciprocals of primes. This sum becomes larger than any arbitrary real number provided that p is big enough. This shows that there are infinitely many primes, since otherwise this sum would grow only until the biggest prime p is reached. The growth of S is quantified by Merton's second theorem. For comparison, the sum does not grow to infinity as n goes to infinity. In this sense, prime numbers occur more often than squares of natural numbers. Brunn's theorem states that the sum of the reciprocals of twin primes is finite.